Banter has just wrapped up.
What banter?
Daily banter.
Oh, every time we come in, we just start talking. We were talking about coats earlier. Just Hope came in all bundled.
Yeah.
Yep. How we doing?
How anybody does in 17-degree weather. My hair's fake and frozen.
Oh, yeah, I get that. Reminds me, one time in grad school, I decided to shave my head. I'd always talked about shaving my head. Did it one night. I may or may not have had a few, but it's entirely possible. Walked out outside the next day, kind of forgot about it. Like, why is my head so cold? Oh, I don't get hair. That was why. I'd always wanted to do it. It was not a good look. I didn't do it again. Wore a hat until the hair came back out again. So, anyway. Tried it. It was one of those things you can try, and it's reversible, right? Hair will grow back, so it's fine.
Thinking about the monk cut, how do you feel about this? So I'm thinking about doing the monk cut. How do you guys feel about that?
I don't know what that means.
Oh, it means top, bald, sides.
Oh.
I could do it.
Looks like something got a little bit too low. Oh, shoot. Any questions at all before we go finish off things today? Posted a review.
It's 25.
The answer is page 25 pages, yeah. There's lots and lots of problems. Well, usually when I teach this class, when I taught this class in the past, I've always done groups first. So I've always had 2 exams over groups. Well, instead of only have one, so just put all of it together. So that's why there's more questions, because there's 2 review sheets combined into one. That's why it's longer. So anyway, let's just review some of the things out of the symmetric and alternating group stuff that we talked about right at the end of the class last time. And then we will talk about Lagrange's theorem today, and that's where we will stop. So this is number 13 on page 234. You've got alpha is equal to 1, 2, 3, 2, 3, 4, 5, 6, 7, 7. Well, that's horrible. I'm going to write it off. This I didn't realize that it had that. That's just dumb. That's annoying. The 10 is one symbol all by itself. It's not a 1 and a 0, unless you... No, that's probably not what they want you to do. The 10 should be just a symbol all by itself. So I would like to put a little space in there so we're not confusing what it is with a 1. Okay. The problem asks you to show that alpha has order 10. And it doesn't matter. This permutation, we can think of as a permutation in S10, since there's 10 symbols are being permuted. But you can also think of it as a symbol in S11 or S12 or S13. Just those other symbols are missing, so they're fixed by the permutation. So this will have order 10 in any permutation group that it makes sense for this to be a permutation of. Right? It has to be a permutation group on at least 10 symbols. It can't be in a permutation group on 5 symbols, is what I'm saying. But the order doesn't change no matter what permutation group you think of it as a permutation in. So you do the problem the same way. Only reason why I'm mentioning it is because the problems, it was stated a little bit weird in the book, I thought. Okay. All right, so before we show that it has order 10, let's remind ourselves about, we talked about even and odd right at the end of class on Tuesday. Right? So if I wanted to write, we can figure it out just from looking as well, but if I wanted to write, say, the cycle 1, 2, 3 as a product of transpositions, how would you write that? Remember, transpositions are those 2 cycles. So how would we rewrite this as a product of transpositions? What would you write? Could be two of them. Good, I agree. There's going to be two transpositions you can use. What two specifically can we use? Okay, I had to do it the other order though, right? Remember, it's function composition, so we work from right to left as we analyze what's going on. I use one as kind of the bridge between the two things. If you send one through, one gets mapped to two. Send two through, two will go to one, but that goes to three. And then three will go to one. So anyway, we've written the 3 cycle as a product of 2 transpositions. So what kind of what kind of permutation is this cycle? Is it even or odd? Even, right? And again, we talked about this near the end of class last time. Any odd length cycle is always an even permutation, and vice versa. So looking at this, going back up here, this will be even. This one's also even. This is even. This one is odd. And think about it, it's just like you would add integers. It's the same idea. If I do even, odd, what kind of permutation are you going to get? Odd, right? Good. So the problem didn't ask for this, but alpha is an odd permutation. Wasn't asked for, but just thought I would mention that since we did that near the end of class last time. Again, you can always do this for any cycle that you have. So for example, if you wanted to write your 2, 3, 4, that would be 2, 4, 2, 3. Just repeat the first thing that appears in your cycle for that many transpositions that you need, and reverse the order of the other ones in your cycle. You can always do it that way. Is that okay? All right. The reason why I wanted to go through this is just to remind a couple of things. If I want to determine the order of a permutation, I need to consider the order of each of the cycles, but I need those the cycles all to be disjoint, or I can't really tell anything, right? We know how to calculate the order of disjoint cycles. How do you calculate the order of a product of disjoint cycles? What do you look at? Good, least common multiple of the order of each cycle, right? Or if you've got multiple of them, you do the least common multiple of all of them. Okay. So the first thing we want to do then is rewrite this thing as in disjoint cycle form, which we've done before, right? When we're done, what combinations of cycles do you think you're going to see? If I'm going to have a least common multiple to be 10, what combinations of things do you think we'll see? Top 5s and 2s, right? We could have some 5s and we have some 2s. We try to throw any other length in there, it's going to change the least common multiple, right? The only possibilities that you have. So, if we rewrite this, we should see 5 cycles and 2 cycles disjoint, right? That's all we're going to have the ability to do. So let's do that. Start with 1. Where does 1 get mapped to? Remember, again, this is one single symbol, right? So 1 gets mapped to 2. Good. Where does 2 get mapped to? Back to 1 again. Do we see why? Running your 2 through here. 2 maps to 3. And then go to here. 3 goes to 1. So it closed it off. Okay. Next symbol we have is 3. 3 goes to, good. 4 then turns around and goes to, so 4, this one it doesn't move, this one doesn't move, this one it goes to 2, then to this one it goes to 3. So closes off again. Yeah. Okay. 5. 6. Good. 6 goes to 7. 7 goes to 8. This is interesting. Oh, maybe it did want it as 1 and 0 and use the symbol 0 as a different symbol. That can't be right. Let me see. I assumed it was a single symbol, but I could be. They may be using 0 for the last symbol. Let me see if they have an example in the book. The problem is that 8's going to go to 9, 9's going to go to 10, and now I've got a 6 cycle. It's not going to have the right size to have order 10. I get aggravated when they go up to 10 symbols. Should have picked a different one. Well, now that I've done it this way, let's ignore the fact that it says do order 10 and just figure out what the order is. The rest of this, 8 should go to 9, we agree. 9 should go to 10. 10 will go to what? 7, which 7 then goes to 5, which closes it off. Yes?
So, I'm a little bit confused.
Mm-hmm.
So, in the previous cycle, the 3-4,
Mm-hmm.
the 4 goes to the 2, which then goes to the 3. So, why didn't we write the 2? Or do you just, bypass that?
So, remember, we're thinking of this as one single function, but the function's made up of 4 compositions.
Mm-hmm.
So, really, I'm trying to figure out what alpha of 4 does. And if I call this, say, beta 1, beta 2, beta 3, beta 4, then this is beta 1 of beta 2 of beta 3 of beta 4 of 4. And so then you would work your way inside out. The first one doesn't move the 4. Right? The second one doesn't move the 4. The third one moves the 4 to 2. And then finally I get to 3. That's why we don't write the 2 in the middle, because I haven't gone all the way through the process yet. I haven't gone all the way through my function composition.
Okay.
I don't think that helped. The look on your face, I don't think it helped.
Okay, so then for the one we just did, the bigger one,
Mm-hmm.
we would write each. I'm confused why we wrote each number then, if that makes sense. Like the 5 to the 6, and then the 6 went to the 7.
Okay, so gotta go right to left, right?
Mm-hmm.
This one doesn't move 5. So 5 goes in, 5 comes out.
Mm-hmm.
5 goes in, 6 comes out. 6 goes in, 6 goes out. 6 goes in, 6 goes out.
Okay.
So that's why 5 went to 6.
Okay.
And then likewise, 6 comes in, 6 goes to 7, and then nothing else moved it.
And then 7 stayed.
Yeah,
Okay.
yeah.
That makes sense.
Yep. That's
Thank
the
you.
idea. Yep. Okay, writing it this way, the order is 6, isn't it? Because I got 2, 2, and 6. The least common multiple will be 6. So they must have this book must want 0 to be the 10th symbol rather than the 10 altogether, which is not the way I would have thought of it, but clearly it's not the way I would have thought of it. Oh, tell you what, why don't we do another one? Treating the 0 as its own symbol, and getting back to the page that I needed to be on for that problem. Sorry. I get irritated with the book and shut it, and then forgot what page I was on. All right. This is 14. Same page. Treat 0 like it's its own symbol. So that second cycle is 5910.
Is the next one 415 or 465?
Oh, good question. 465. Okay. First, let me ask you, is this even or odd? That one should be pretty straightforward, hopefully. Why? Other way around. There's 3 evens and 1 odd, right? Isn't it? Or 3 odds and 1 even? Sorry, whichever way I said this. Yeah, one of us is right. Those 3 are odd.
Yeah.
Right. So 3 odds and 1 even.
Wait, 5, 9, 10?
It's 5910. We're treating 0 as its own symbol.
Oh, okay, sorry.
That's okay. I think that's the way, given what the previous problem was, and we didn't get the same answer that the book said we should have got, I'm assuming they're treating 0 as its own symbol and not 10 altogether. I hate using 0 as a symbol because if you put it next to the 1, you don't know what you're supposed to be using it as. If you want to use a different symbol, literally just, there's got a whole bunch of letters, choose one. Pick one, it doesn't matter what it is. All right, so this is odd, odd, even, odd. So it's odd. We agree with that? Okay. All right. So let's do the disjoint cycle form. Start with 1. What does 1 get mapped to? 2? Because the other one's fix 1. Oh, no, sorry. Nope, 1 gets mapped to 0. Sorry. Try that again. Yep, sorry. See, this is where I got it screwed up last time. All right, try that again. Where's 0 mapped to? 5. 5 goes to...
I keep going left to right. 6.
I think 9 was right.
Okay. I'm getting so confused for no reason. Okay, yeah, it's 9.
So 5 goes to 6. 6 goes to 5.
5
5 goes to 9.
Okay.
And 9 stays there. Yeah.
Okay.
Yes. I agree with you. It was 9. Like, no, wait, you were right. All right. Where does 9 go to? 2. Everybody see why? 2 goes to 3. Whoa, what just opened up? Go away. 2 goes to 3. 3 goes to 6. 6 goes to 7. Okay, then I really don't know what they're doing in this book. 7 goes to 8. 8 goes to 4. 4 goes to... It does go to 1. Good. And that has length 10. So its order is 10, because that's it, right? We got every symbol in there. Okay, then I really don't know what this book's doing, because it says it's supposed to have order 21, which it does not. I really have no idea. That'd be a 3 and a 7, which will give you 21.
I'll just do it again real fast with 10 instead.
Yeah, that's it. Okay, they're using the same convention that we're talking about these being compositions of things, 1 goes to 0. 0 goes to 5. 5 goes to 6, which goes to 5, which goes to 9. Yeah, I give up. Okay, we're doing it right. I don't know why the book says it has order 21, because that's a 10 cycle. It has order 10. Anyway, are you okay with getting the process down? Because I don't want to make it more confusing because the book has got issues. Is this process okay? I don't want this process to be hard because there will be one on your test that's like this. You? We're okay? Okay. Good. All right. I think that's all we really need to talk about. This is really what I'm most interested in with being able to do things in permutation groups. Make sure that you can write a permutation and start with a permutation, be able to write it as in cycle notation. If I start with a product of cycles, make sure you can write it in disjoint cycle form like we were doing here. Once you have it in disjoint cycles, know that how to calculate the order. Okay. Know that it's and then also know how to tell if the permutation is even or odd. And can you write it as a product of transpositions? Okay. Like we mentioned last time, permutation has to be even or odd, but can't be both. So it's one or the other. Okay. So, for example, if I could write something as a product of 12 transpositions, I can't write it as a product of 7 transpositions, but maybe I could write it as a product of 18 transpositions. Because 12 and 18 are both even, but 7's odd. Once I know it's even, then I have to use an even number of transpositions when I'm done. Okay. The identity is an even permutation. In order for permutations to definitely commute, you need to have them as disjoint cycles. They may or may not commute if they're not disjoint. But if they're disjoint, you know they commute. So generally speaking, cycles, permutations don't commute, but if they're disjoint cycles, then they do commute. That's the big things that I want you to remember for them. Pardon me. All right. One of the other theorems that I think I briefly mentioned, that I will briefly mention again, but not going to expect you to remember, is that every single group can be embedded in a permutation group. There exists a group of, bless you, there exists a group of permutations that you can, whatever group you have, you can think of as a subgroup of that permutation group. It's called Cayley's theorem. The idea behind that is then if you can prove theorems about the bigger permutation groups, then you've basically proved about every single group. That's the idea behind that. So anyway, we're not going to do anything with it, but it is big enough for me to mention. It's usually one of those things that if somebody bothered to name the theorem, you should probably remember it. If it has a name, it's probably fairly important. Just kind of a rule of thumb. I don't have any theorems named after me, so. Working on it. All right. So, last section we're going to talk about is 8.1.
Would it be like J-Sticks theory?
J-Sticks theorem. That'd be funny. If I had one to name, that would be what I would name it. Even better is usually when, not usually, but a lot of times when a theorem is named after somebody, they're not the one who proved it. They named it in honor of somebody else.
That's sweet.
Isn't that nice? No one likes me enough to name a theorem after me either, so.
I'll make J-Sticks theorem.
There you go. There you go. I like it. Thanks. All right. Anyway, so going back to the idea of congruence, we talked about equivalence relations, congruence relations before. We're just going to define congruence in a specific way. So as a definition, we're going to let K be a subgroup of a group G and we'll let, I'll call it G and H be in capital G. The definition is then G is congruent if I can write, it would be very helpful, to H modulo K if and only if, pardon me, that GH inverse is back in K again. G may not be in H, excuse me, G may not be in K, H may not be in K, but this product in this fashion is back in K again. So let me give you an example here of what this might mean. So let's say we have our group is D4, and let's let our K be the subgroup that contains the 0 and the 180-degree rotations, the flip about a horizontal line, and the flip about a vertical line. Certainly, R90, not in K. Diagonal flip, not in K. But we should be able to figure out, hopefully, that this product is back in K again. Well, so I'm just doing this computation of first element, second element, inverse, right? What is the inverse of any flip? Itself, right? The inverse of a flip is a flip, right? So this just says do R90 and then the diagonal. So rather than trying to go back through notes and trying to remember what the different things are, let's just see if we can figure this out. First, we would do the diagonal flip, which is about that diagonal, right? We agree? So we end up with the 1 and the 3 change places, but the 2 and the 4 stay the same. And then we do the 90-degree rotation. So the 4 is here, the 3 is here, the 2 is here, the 1 is here. Looking back where we started, what single reflection is that? H, right? So this is H, which is back in K again. So we say that R90 is congruent to D modulo this K. Why do we use that language? Well, remember when we did mod out by an integer, we said that two integers were congruent to each other modulo another integer if their difference was divisible by that integer, right? A is congruent to B mod n if A minus B is a multiple of n. N divides A minus B, right? Well, thinking about our knowledge of cyclic groups, multiples of n are just a subgroup of the integers, right? Every subgroup of the cyclic group is cyclic. They're generated by a single element, and it's just the multiples of those things, right? So multiples of n is a subgroup. GH inverse written additively is what? If I change that from multiplicative notation to additive notation, what would GH inverse be? Instead of writing multiplication, we would write, exactly. Remember, instead of multiplication, if it's written additively, we use plus, but if we went inverse, we use minus. So G minus H would be the additive notation, which is the same thing as we use for A is congruent to B mod N, right? A minus B. Okay. So that's why we use the same words. We're just changing it over to a more abstract. So, good news is that it behaves just like congruence modulo an integer is. We're just doing it with respect to a subgroup. So, theorem, pardon me. So, the theorem is that congruence modulo a subgroup is an equivalence relation. You would prove it just like you would prove any other equivalence relation. It's going to look a lot like what we've already done for congruence modulo an integer or congruence modulo an ideal. It's the same type of proof. It's just that it's written multiplicatively instead of additively. So reminding ourselves again of how to prove something is an equivalence relation, what 3 things do you have to show? Good. So if we want to do reflexive, I should say it's an equivalence relation on the whole group, not just the subgroup, but the whole group. Okay. So for reflexive, we're going to start with some element in the group. I need to show that it's equivalent to itself, right? So let me scroll back up to the definition. 2 things are congruent modulo the subgroup if when I take the G times H inverse, I get back in K again. But I want to show that something is equivalent to itself. So rather than GH inverse is back in K, what do we need to show? GG inverse is back in K. Well, what is GG inverse equal to? The identity, and what do we know about the identity? It's in every subgroup. Fantastic. Good. That's exactly right. So we have reflexive. Yep. I'm going to shut the door because like I said, it'll work at least it'll bug me. All right. So let's do symmetric. Remember, for symmetric, we get to start with 2 things are related, and then we want to show it the other way around, right? So let's suppose that, and we actually use the same notation, at least the book does. Let's say we have G is congruent to H mod K. If G is congruent to H mod K, what do we know? Good. GH inverse is in K. What do we want to show? Okay, good. We want to show that HG inverse is in K, right? We want to reverse the roles of H and G. Well, if I want to reverse the roles of H and G, what operation do you think we can apply to this product that ends up getting us exactly what we wanted? I need to reverse the role. I need to reverse the product and reverse the inverses. So what operation can I apply to this? And reverse the product and reverse the inverses. Yeah, you just take the inverse. Good, exactly right, right? Remember when you do the inverse of a product, it's the product of the inverses in the reverse order, which is literally what we want, right? So if I take the inverse, how do I know that the inverse of that product will be back in K again? Well, what kind of a thing is K? It's a subgroup, which means it's a group itself, right? Groups have to have an operation that's associative. You have to have an identity, and everything has to have an inverse, right? So it's closed under inverses. We have GH inverse. Inverse is also an element of K, or H inverse G is in K. And this is because K is a subgroup. Hence, G, other way around. H is congruent to G mod K. That part okay?
Why wouldn't it be HG inverse?
Oh, you're right. It is, which is what I wanted. Sorry. It was right in my head. It just wasn't right on the paper.
I'm gonna say that when I turn my exam.
During your exam, it's right in my head.
Well, truth is subjective anyway. Really, it's a word.
Okay, is this okay? Thank you for catching that. All right, last one. For transitive, what do we start with?
Two things are congruent, and then it's congruent to another thing, and then the first and the third thing is congruent.
Good. All right, so do what Laney said. Let G be congruent to H and H be congruent to J. What do we want to show? Yeah, G is congruent to J. Fantastic. First statement tells you what?
GH inverse.
And the second one tells you?
HJ inverse.
Okay. This is our definition of being congruent, right? We agree? Okay, cool. All right. Pardon me. What do we want to show? What do we want to get to?
GH inverse. Oh no, GJ inverse.
GJ inverse. How are we going to get to GJ inverse? Yeah, just multiply them together, right? Now we need to make sure it's back in K again. But what kind of a thing is K? It's a subgroup. So previous step, we used the fact that subgroups are closed under inverses. Next one, we're going to show that subgroups are closed under products. Yeah. Notice that sounds a lot like your two-step subgroup test, right? To show something is a subgroup, you show that it's closed under products and closed under inverses. We're using that same thing, right? Two-step subgroup test is an if-and-only if statement. Okay. All right, so now GH inverse HJ inverse is back in K, since K is a subgroup. Hence, oops, GJ inverse is back in K. It's a funky looking G. What are you doing? Stop. And she is congruent to J mod K. My other computer stopped projecting, so I started went to an old one. This one's being clunky. I'm gonna get a new one. Not that it helps you for this class, but we're gonna get a new one. Who has me next semester? Do they have me next semester? Wow. Seriously? We'll be all sad. I won't see any of you next semester in class?
Well, the semester after, you'll find plenty of me. The next semester, I think the only math course I have is advanced calc.
Okay.
So see two of you there.
Maybe, I guess, if it's a possibility for the intern, like the teaching internship thing.
Well, that is true. Yeah, if one of you are doing the teaching internship with my class, then you'll see me.
Yeah.
Yeah, that's right. All right. Now that we have an equivalence relation or a congruence relation, we have equivalence classes or congruence classes, right? So remember that when you talk about an equivalence class of something, that means the set of all things that are related to it, right? So in this case, we would have it this way, wouldn't we? That's what we mean, right? Now, we know that we can write this as, well, I could either write it as AG inverse or GA inverse, right? So I'll do GA inverse is in K. Doesn't really matter which way I write it, but I'm going to write it this way to help with the notation here. To be in K, that just means I'm equal to K for some K, oops, little k. Oops. In capital K. And then do one more step. I know I'm writing this really weird, but I'm getting to a point, I promise. All right. So let's look at this last condition. When I look at the equivalence class of A, remember again, that's everything that's related to A. We can boil that down to, that really means that thing that's related to A is something from K times that same A. Okay? So let's look at that first example that we did, where we had G was D4, not D9, which is what that looked like. D4, our K was R0, R180, H, and V. And I want the equivalence class of R90. That was one of the elements we started with, right? Notice that this says that if I'm going to be related to my A, then it has to be something from K times A. So notice I'm on the right-hand side, right? So it's K times A, not the other way around. You can do it the other way around too, but you have to change your congruence relation. So this says that we do K times A, so I'm going to multiply on the right. So the way that I can generate this is just take this entire subgroup and operate it on the right with that element. So the notation looks a little funky, and I'm going to go back and denote the notation here, or write down the notation specifically in a minute. This says do the entire subgroup and multiply it by that element on the right, and just run it through. Okay? So if I do R0 times R90, what do we get? R90. If we do R180 times R90, what do we get? R270, right? We agree? Okay. Now do a little bit of work to do the other ones. We would first rotate and then do a horizontal flip. Which one is it? It's diagonal. Right? That one's fixed, yeah. So then we would get D. I bet you can guess what the other one is. What's the only element we haven't talked about yet? Looking at everything that's on the board. The board. Everything that's on the board. What's the only one we haven't talked about yet?
D. I don't know.
Yeah, the D prime, the other one, right? Let's make sure that's right. Rather than this was doing horizontal, we do vertical now. That is the other one. I already knew that ahead of time. Let's think about why I knew that ahead of time. I am generating an equivalence class. The subgroup itself is also an equivalence class. It would be the equivalence class of, say, the identity. Right? If I run the identity through everything, I don't change anything. The subgroup itself is an equivalence class. For any equivalence relation, what has to be true about two equivalence classes? If I take two equivalence classes for any equivalence relation, there's nothing special about this one. Two equivalence classes for any equivalence relation would have to be true. So you got an either or situation.
Either they all intersect or one of them intersect.
Correct. Either they're exactly the same equivalence class or they're completely disjoint from each other. Right? Equivalence classes are either identical or disjoint. The only choices you have. Were these going to be identical as soon as I did this one? No, because that's not in there, right? So they're not identical equivalence classes, so they have to be disjoint equivalence classes. It's the only choice you have. We didn't say anything about the sizes yet. We will do that here in a second. That's the important part of Lagrange's theorem. But since we have an equivalence relation, equivalence classes must be distinct from each other and disjoint from each other when they are different from each other. They have to be disjoint from each other when they're different from each other. Turns out, the way we're doing this, they also have to have the same size. Okay. But in particular, I knew this was probably my last one because that was the one I hadn't used yet. That makes sense? Okay. All right. So we give equivalence classes here a special name. Oops. The definition. For K, a subgroup of G and little g, an element of G, the right coset of K generated by G is, we write it as kilograms, what it looks like to me. But kg, you just put it on the right hand side. And this is the set of all little k times g such that k is in k. How do you think the left coset of k would be defined? Yeah, put the k on the other side. Exactly right. That equivalence relation comes up. We know how we did this one. We did GH inverse. We could have done the same thing as G inverse H. That's also going to be an equivalence relation, and you can generate left cosets just like you do right cosets. Now, what we're not going to get to this semester is when you have left cosets and right cosets being equal, that's a special type of subgroup you get that's referred to as a normal subgroup, which you need to form quotient groups, like we did with quotient rings. We just don't have time to get there. This would be the next section after this one. Yeah. That's where the left and the right coset ideas come from. However, now that we have either left or right cosets, we get an important theorem. Oops. This is what's known as Lagrange's theorem.
Immediately have flashbacks to the Laplace's theorem.
Well, you also do Lagrange multipliers in Calc 3. Same guy.
Busy guy.
Busy guy. Yep. Yep.
They need to guide themselves. Okay.
All right. So Lagrange's theorem says that the order of a subgroup divides the order of the group. Now, just to review real quick, we've already showed this for cyclic groups. However, for cyclic groups, we had the added condition that said if you have a divisor of the order of the group, there exists exactly one subgroup of that order. That's special for cyclic groups, okay? All Lagrange's theorem tells you are what are your possibilities for the order of a subgroup. It doesn't say that there has to be only one, and it does not say there has to be any that actually even exist. Okay. We're not going to show this because I don't feel like going through it all. But remember I told you about the alternating group? That was the set of all even permutations. Right? The alternating group was a set of all even permutations. Okay. It had half the size of your permutation group. Okay. Hi, Miss Anna. How are you?
I'm struggling.
Your alternating group has half the size of your permutation group, so what order is this group have? 4. It's a subgroup of S4. What's your size of S4?
8. Nope.
That's D4.
Okay.
Oh, it's 4 factorial.
Yeah, it's 24, right? It's 4 factorial, so what size does this have?
12.
12, yeah, half of 24. Hey, we got there. Yay! Okay, so the alternating group on 4 symbols has 12 elements in it. Okay. I know we haven't done a lot with it, but this is the example I want to give for, pardon me, want to give that show that has no subgroup of a particular divisor. What are your divisors of 12?
6.
Good. Okay, cool. Now, just to show some different things here. Certainly there's a subgroup of order 1. And no matter what group you have, there's only going to be exactly one subgroup of order 1. It'll be the subgroup that contains the identity. Okay. Also, there's exactly one subgroup of order 12 in this case, because if you have a group of order 12 and you're a subgroup of order 12, you have to be the whole thing, right? Hopefully those two are obvious, right? There's only going to be one subgroup of order 1. There's only going to be one subgroup of order the whole group. Okay. Now, for 2, I can find a few. Let me show you 2. Remember, I need to do even permutations. The alternating group is a set of even permutations, right? So if it's going to be an even permutation, I have to be able to write it as an even number of transpositions. That works, doesn't it? We agree? Right? And this has order 2. Why does this have order 2?
Each has 2 elements, but least common multiple of 2 and 2 is 2.
Fantastic. They're in disjoint cycle form. Each of them are 2 cycles, so each of them are order 2. Least common multiple is 2. Right? Good so far? Okay. I can make another one. Can you tell me another one that's going to look like this but be a different subgroup? looks almost like this, but be slightly different. Basically, I need to use a different element.
1, 3, 2, 4.
Yep, 1, 3, 2, 4. This also has order 2, so it forms a 2-element subgroup. Right? And it's definitely different from that one because this 1 goes to 2, this 1 goes to 3. So they're different subgroups. Right? They're different elements. I bet you can find one more. Hey, there you go. Okay.
I'm blanking. What was that symbol that you keep writing?
Oh, that's the identity permutation, the thing that fixes everything. I'm just writing an epsilon. That's pretty standard. Rather than writing an E, since it's a permutation, we typically use Greek letters, so we change the E to an epsilon. Sorry.
That makes sense.
We have to be fancy.
I figured it's a notation thing, but I also
Yep.
figured I should probably know what it does.
Yeah. So one of the reasons why I wanted to mention this, besides reviewing a little bit with permutations, remember for cyclic groups, it says there's exactly one subgroup of the order that of an order that divides the order of the group, right? This only has 3 subgroups of order 2. Okay, so it's not true for every single group. That makes sense? Okay. Likewise, if I have a group of order 3, here's 1. A 3 cycle is an even permutation, right? Odd length cycle is even permutation. I'm also doing this to help review a couple of things as well, right? Odd length cycle is even length permutation, but odd length, the length of the cycle is the order of the element, right? So the element 1, 2, 3 has order 3. So if I do 1, 2, 3 and compose it with itself, I'll get 1, 3, 2. I'll get the other, and kind of get flip the 3 and 2 around. You can check that, or remember that if it's going to be a subgroup, its inverse has to be in there. If I do the inverse of any cycle, I can just reverse the order, right? 1, 2, 3, the inverse would be 3, 2, 1. But since it's a cycle notation, if I cycle my things around, I get the same exact thing. Right, so I just took the 1 from here and cycled it around here, I get the same exact cycle. This would do the same thing as that as well. They have the same outputs, right? So I just wrote it the other way. Anyway, that gives me 1. You can probably think of another one. One, 2, 4, and then 1, 4, 2 would be in there as well, right? So I can have a second subgroup of order 3. This one, I'm basically showing you that there is one of each of these orders. If I take those 3 elements of order 2 and put them all in the same group, I end up making another subgroup this way. Notice here, this is a subgroup of order 4 that I wrote down, but each element besides the identity has order 2, so it's not cyclic, right? So this is a different group of order 4 than what would be the cyclic group of order 4, right? I'm going to write down a Cayley table for that here in a minute anyway, but just to remind, just to tell you that this really is it's a non-isomorphic group to Z4. Okay. What haven't I taken care of? That one, right? We're not going to do it, but there are no subgroups of order 6 in A4. You can show that it has no subgroup of order 6. Just by the way of the way that you'd have to make sure that things are closed, you'd have the wrong size of permutation, so then you have to add something else in there and you end up with the whole group. So you can actually show that this has no subgroup of order 6. Okay, so again, just to emphasize, and then we're going to go prove Lagrange's theorem, because it actually doesn't take that long, even though it's important. Just to emphasize, for cyclic groups, yes, if you have a divisor of the order, then you get a subgroup of that order. And in particular, you get one subgroup of that order. But for groups in general, that's not true. Okay? For groups in general, just because you have a divisor of the order doesn't mean there's necessarily a subgroup of that order. However, the order of the subgroup does have to divide the order of the group. So you know automatically there's not a subgroup of order 5 because it doesn't divide 12. Okay. However, 6, there may or may not be. It turns out in this case there's not. That makes sense? What the difference between those two things is? Sure, yeah. So I'll go through the whole thing again. For cyclic groups, every divisor of the order of a cyclic group guarantees that there's exactly one subgroup of that order of that divisor. Okay. So if this were a cyclic group of order 12, you'd have exactly one subgroup of order 1, order 2, order 3, order 4, order 6, order 12, and that's it. Okay? That's all you get. That was when we were doing those subgroup lattices in the last homework too. Okay. For Lagrange's theorem, just because you have a divisor of the order does not mean you have a subgroup of the order that is that divisor. So A4 is an example where you do not have a subgroup of order 4, or excuse me, order 6. Okay. However, it does work the other way. If you have a subgroup, then the order of that subgroup has to divide the order of the group, without a doubt. Okay? All right. So let's prove Lagrange's theorem. So we know the set of, if we have K as a subgroup of G, then we know that the set of equivalence classes modulo K, form a partition of G. Remember what we mean by a partition for a set? A partition of a set is a collection of non-empty subsets whose union is everything and pairwise intersection is empty. That's what we mean by partitioning up a set, right? So, I mean, the name comes from the fact that something like that would partition it, right? That would be a non-empty collection of subsets of the set 1, 2, 3, 4, 5, 6, 7 that has union everything and intersection nothing, pairwise intersection nothing. That's what we mean by partition, right? Okay. So remember that the equivalence classes are those set of right cosets. The equivalence classes are the right cosets. So choosing distinct right cosets, I don't even need distinct right cosets, but choosing distinct right cosets to make sure we don't have those overlaps, we can write G as the union of right cosets. Remember, equivalence classes are always non-empty because the equivalence class generated by the element's in there, right? So if we think of our equivalence classes as cosets, then our group can be written as the union of those cosets, But what do we know about those cosets? Those cosets have no overlap, right? You agree? Yeah? Okay. Since I'll write KA1 intersect KA2 is empty, when A1 is... I have to be a little bit careful. This is why I said distinct cosets. All right? It's possible that two different elements generate the same coset, so we want to make sure we have distinct cosets. So I'm choosing representatives that generate distinct cosets. We have that the order of G to be the order of the union. I'm writing things finitely, but this works for infinite as well.
Are we writing the capital K because we're doing everything in K?
Yep, we're writing the capital K because we're doing everything in K. That's exactly right. Okay. This is why we need to make sure that we have disjoint union. Remember that when you count number of elements in a union, you do the elements in the first, you count the number of elements in the first set plus the number in the second set, but what do you have to subtract off if you do counting in a union? The overlap, right? You have to subtract off the intersection, right? I'm sure some of you talked about that in this group this semester. Order of a union, the sum of the orders, and then, or the cardinality of the union, I guess I should say. Anyway, doesn't matter. But since I have no overlap, I can just add them all together. Okay. What are we trying to show? What's the conclusion of Lagrange's theorem? The order of the subgroup divides the order of the group, right? So looking at this sum, I want two things. I want one of these better be the order of the whole subgroup. The other thing I want is that each of these really is the order of the subgroup, right? So that I'm just adding the order of the subgroup over and over again to itself. And then I have what I need, right? Because then this would be a multiple of the order of the subgroup. Right? Well, what is always going to be one of your cosets? Well, one of your cosets is always going to be the subgroup itself. What's going to generate that coset? What can you multiply every element of K by and guarantee that you get K back again? The identity, right? So one of these has to be order of K, and then I have the rest of them, right? One of them has to be the order of K, because one of them has to be K in particular. I need the rest of these all to have the same order. To do that, let's define a function f from K to a coset generated by A. Where do you think I might want to map an element of K to? I think I'm going to be a little bit more specific than that. I want to make sure I land in the coset generated by A. Yeah, I probably should do KA. Good. I want to show that each of these cosets has the same cardinality, the same size, the same order as the order of the subgroup. So what kind of function do we want f to be to guarantee that these two things have the same size? What kind of function do I want? Specific adjectives, a specific adjective or two adjectives that when you put them together means the same adjective as the third one that I'm looking for. Okay, that's the idea. What's properties vice versa? It doesn't have to be operation preserving. You're thinking the right way.
All right. Surjective and injective.
There we go. Yeah, surjective and injective make bijective. Yep, exactly. I want a bijection, right? If I have a bijection from one set to another, they have to have the same size, right? So I want this to be a bijection. I want to be 1-to-1 and onto. This is onto by construction. How do I create all the elements over here? I multiply every element of K by A. So if I take a KA in the output set, I map K to it. Onto by construction, isn't it? 1-to-1. That's also pretty straightforward. Remember to start with 1-to-1. You start with two outputs being equal. How do I get K1 as K equal to K2? What would you operate on both sides? What would you multiply on both sides? A inverse, good. This is why we need groups, by the way, because we want to make sure that everything has an inverse, right? Right? This wouldn't work in general if we didn't have an inverse of every element. But operate A inverse on the right on both sides. Just to emphasize that, I'll do that. I will skip the next, the next steps that would be involved. Operate A inverse on the right, not the left. It has to be on the right. You would reassociate, get the identity, and then get the K1 equals K2. All right, so now we have a bijection. So now going back up to the other part, I can replace each of those, what we had before. I got to this point. Good grief. I can replace each of those other coset sizes with just the size of K. I'm not replacing each of the cosets with K, because remember we started with distinct cosets. All we're saying at this stage is that all of the cosets have the same size. And now we have what we wanted. The order of K divides the order of G. We have what we wanted. That's exciting. We got what we wanted. Merry Christmas, everyone. All right. One last thing. As a definition, the index of a subgroup is the number of distinct cosets that subgroup has. Distinct cosets of the subgroup. We denote it with that brackety notation. Bless you. We denote it with that brackety notation. This brackety notation here would be that n value that was back up in the proof. So the formula relating these things is that if you take the order of the subgroup and multiply it by the index of the subgroup, you get the order of the group. If your subgroup is finite, you can divide both sides by the order of K and get that the index is just the order of G divided by the order of K. Now, of course, if it's not fine, if it's infinite, then you get infinity over infinity, which from calculus is an indeterminate form, so we don't do it that way. But that's just the definition of what we mean by the index of a subgroup. So.
I feel like the L'Hopital's rule here is going to be a little rough.
Yeah, L'Hopital's rule would be a lot of rough. Calculus would be hard on discrete structures like this, but there is the idea of doing, I think it's called projective limit in algebra. I think that's the right word. It's been a long time since I've done it, so I can't remember if I got the right word or not, but we're not going to do that, obviously, because we are now officially out of time.
No.